Here's a function from the unit circle into 3 space. For each point on the circle, given by an angle theta, the coordinates of the image point are 2 plus cos 3 theta times cos 2 theta, 2 plus cos 3 theta times sine 2 theta, and sine 3 theta. Well, have you any idea what the image of that function looks like? Not many people can glance at a formula like that and visualize the image curve. But as a matter of fact, those rather complicated formulae visualize as this very simple curve in 3 space. It goes round twice and bobs up and down 3 times at the same time. And as a matter of fact, it has a very obvious global property, which you can see if I start to deform it a bit. It has a knot in it. What do I mean by saying it's knotted? Well, I mean that however much you move it around, you're not going to be able to get rid of that little knot. Of course, that isn't a proof. And anyway, it's not going to be obvious when I have a look at something whether it is going to be knotted or not in that sense. For example, is this thing knotted? Well, as a matter of fact, it's just another copy of the same knot we've just seen, and it's called the trefoil knot. But what about this embedding of a circle? Is it knotted? Well, as a matter of fact, this one isn't knotted. It's equivalent to the standard round circle. So that's what this program's about. We're interested in the placement problem for the circle in 3 space. We're interested in embeddings of the circle in 3 space under homomorphisms of circles of 3 space. And we want to know whether an embedding is knotted like this or unknotted like this. And we're going to look at this problem in this program, and we're also going to look at the associated problem of links, of embeddings of more than one circle in 3 space.
Well, a knot is a rather complicated thing in 3 space. How much simpler it would be if we could have a picture, a 2-dimensional diagram of a knot. Just talk about that. Well, in fact, that's what we do. And here we have an example. It's a projection of a knot. And then we can do our calculations on blackboards or pieces of paper. It's much simpler. However, there is one complication. I mean, that's a projection of a knot. But here we have another projection. It looks very different, but in fact, it's a projection of the same knot. And in fact, here is yet a third picture. Again, it looks very different, but they're all equivalent in that they come from the same knot. So what we're really discussing are equivalence classes. Projections of a knot are equivalent if they come from the same knot. That again seems a bit difficult, because how do we get from one member of the equivalence class, from one projection of a knot to another? I mean, it looks as if it's very complicated to get from this picture to that. But in fact, it's not. You can get any projection to go to another one by just using sequences of 3 very simple moves. And they're called the Reidemeister moves. Well, these Reidemeister moves go by the name of the twist, the tongue, and the slide. And they're very simple, so let me describe them in a bit more detail. First of all, the twist. Here I have a piece of string, and it's very important to realize that everything I do here is done locally. It doesn't affect anything that happens outside this area. So I can simply introduce a twist, you see, or I can do the inverse operation, untwist, and clearly that doesn't affect anything. So that's the twist. Now what about the tongue? Well, here I have locally, again, 2 strands of my knot, and I, of course, can tuck this strand under that. That doesn't affect anything. And the inverse operation, I can untuck it again. And the third one, well, the slide. Here I have 3 strands of my knot. Well, I can slide the lower one under the other 2, or the inverse operation, I can slide them back again. Well, you can prove that you can tangle or untangle anything to get from one projection to another by just using sequences of these 3 moves. But we can't prove that here at the moment. What you can do is convince yourselves of it by trying it with some strings at home. What I'll do is a couple of examples. I'm going to show you that I can get from this configuration of the trefoil knot to another configuration just by using a sequence which consists of these Reidemeister moves. Well, the first thing I'll do is the slide. I'll slide this strand over these 2. Now that introduces a twist, so I can untwist that. And now here I have another slide, which I can slide that And now I've introduced a twist. I can untwist that. And now what have I got to do? Well, it looks as if I have a tongue move to do here. And now I have a tongue. And make it look a little bit neat. And you see, well, it's slanted, but I can straighten it up. And I have precisely the same configuration of this trefoil knot as the one over here. And let's look at another example.
So what we'll do is we'll avoid the problem of proving that any homeomorphism of R3, any tangling or untangling of a knot, can be realized by Reidemeister moves. We'll actually define a knot to be an equivalence class of knot projection such as this under Reidemeister moves. So it's a bit like a geometry. We've got configurations, that's knot projections, and we've got allowable transformations, the Reidemeister moves. And our task is to prove that there are two different configurations, two different knots. Well, taking our hint from geometry again, what we'll need is an invariant. What we need is some property of this configuration which is invariant under Reidemeister moves and is not shared by this configuration. And that'll prove that this is genuinely knotted. Well, it turns out that there is such a property, and it's a very simple one called three-colorability. And what it consists of is it consists of coloring the arcs of the diagram using three colors. And the essential thing is that you've got to use all three colors. And there's various rules for what to do at a crossover, like here. You're allowed to use just one color, or you're allowed to use all three colors, but you're not allowed to use just two colors. So let me see if I can finish the coloring on this diagram here. Well, let's think about this segment here. If I make that red as well as this one, then this is going to have to be red by the rules because I've got already two segments there colored red, so the third one's going to have to be red. And then that means it's all red, so I won't have used all three colors. So let's actually make this segment a different color in an attempt to use all three colors. So now I've got two colors used at this crossover here, so I'm forced to use the third color. So I put down the third color. And so luckily, we've got all three colors used at each of the three crossovers, so we have got a genuine three coloring. Well, let me try another example. Let's try this knot projection. I'll start by coloring this long segment red. And now, if we look at this crossover here, we've got two segments coming in colored red, so I'm bound to make the third one red. So that's red as well. Now I've got a choice. It's much like before. If I choose this to be red, then that'll have to be red, and I won't have a three coloring. So I better choose it to be a different color. So let's choose it to be blue and see what effect that has. Well, now I'm forced to have green here by looking at any of the crossovers. And once again, I do get a genuine three coloring. Well, that's lucky because, you see, if you look down here at the rope picture of the same knot, you can see that by untwisting it, it's in fact just another trefoil, and the mirror image, in fact, of that one. So if one's three colorable, the other one ought to be, otherwise we won't have an invariant. Let me try on this one here. Once again, we'll start by coloring the longest segment in the picture. So it actually goes all the way around here. And now, having colored that red, I've got red at two of the strands of this crossover here. So I've got to have that red, and then likewise I've got to have this red. So the only possibility is that it all comes out one colour. In other words, it isn't three-colourable because I haven't used all three colours. For a final example, let's try this knot projection. And let me start by colouring this one red. Now, I've got a choice. Supposing I make this strand red, then looking at this crossover and this crossover, I can see that these two strands have got to be red. And then this strand will have to be red, and the whole thing will be red. So if I make this strand red, it'll all end up red, so I'd better make it a different colour. So it doesn't matter which colour I choose, let's choose blue. So let's make that strand blue. And now it's forced, because you see, looking at this crossover here, I'm forced to have green there. And looking at this crossover here, I'm forced to have green. And then if I look at this crossover here, I'm forced to have red on that strand. And now I'm out of luck, because at these two crossovers, I've only used two colours, not all three. And that was the only possibility, so I've actually proved that this knot projection is not three-colourable. As a matter of fact, the previous knot projection, which was also not three-colourable, is in fact a projection of the unknot. You see that very clearly if you look at the rope copy down here. It comes undone very easily. So that's a good indication that three-colourability should be an invariant of knots. It should be invariant under the Reidemeister moves.
Well, let me try and show that. Let me try and show that what I do here locally doesn't affect the global colorability of the knot. Well, let's look first of all at the twist. Supposing I have the twist and, well, that can only be one strand of one color. In this case, I introduce a twist. Well, by the rules, it can only be all the same color. And so, really, I haven't done anything. I have a green strand coming in, a green one coming out before, and the same after. So this local operation doesn't affect the global coloring of the knot. Now, what about the tongue? Well, I suppose there are a few cases. The easiest case is if it's both the same color, and then, well, everything would be the same color here, and so that wouldn't affect anything. So let's try another case where this is red, and this is blue. Now, the top strand here is red, corresponding to that red one. And here I have a blue one coming in. Now, by the rules, there must be a third color introduced at this crossing point, so I must introduce green here. And then again, by the rules, I must introduce blue. So, in fact, this really brings me to the same picture, a red and a blue coming in and a red and a blue coming out. So that local operation doesn't affect the colorability. Well, you might say, hey, look, you've introduced a third color. Perhaps this wasn't three-colorable before. But don't forget, these are two strands of the one knot. So, in fact, these must have met elsewhere in the knot, perhaps each other. And so at these crossing points, for example, here, red and blue, at a crossing point such as that, the third color must have been introduced anyway. So again, this local operation won't affect the global colorability. Now, what about the third case? Well, this is a bit more complicated. There are lots of different cases for the slide, but let me take, for example, this is blue, and say this is red. Now, by the rules, where this crosses, I must introduce a new color, so this has to be green. And supposing I have green coming in, well, again, at this crossing point, this has to be blue. And now I really, because I have blue here and blue here, I can only have blue here. So that's one coloring. Now let's see, if I have this blue, corresponding to this blue one coming in, and if I have this red, corresponding to the red one coming in, and what about the green one coming in? Green. Now let's see what the rules tell me. Well, at that crossover point, I must introduce the third color red, and at this crossover point, I've got to introduce the third color green, and this is another crossover point, and I have to introduce blue. And this is forced on me by the rules. Now let's see, what have I got? Before I had red, green, and blue coming in, and two blues and a green coming out. Here again, I still have red, green, and blue coming in, two blues, and a green coming out. So you see, this local operation doesn't affect the global coloring. So that demonstrates that these three Reidemeister moves don't affect the colorability of my knot.
So now we can prove that the trefoil knot really is knotted because we've got an invariant we can use. We've seen already that the trefoil knot is three-colorable in this projection, and we've seen that the unknot is not three-colorable in another projection, and in this projection it obviously isn't three-colorable. So this projection is three-colorable, this one isn't. Three-colorability is invariant under Reidemeister moves. They can't be the same. The trefoil knot really is knotted. But unfortunately, three-colorability doesn't always help to distinguish things which are, in fact, obviously different. Here we have an example of a couple of links. Now, a link is a projection of one or more circles like this, and it's defined, just as we did for a knot, to be an equivalence class of projections under Reidemeister moves. This link of two components here, of two circles, and this link of two components are obviously different, because this one up here is genuinely linked, whereas this one obviously isn't. But three-colorability isn't going to help us prove that, because you see, the only way you could color these differently is to give them different colors, and then obviously the rules are broken at these crossovers. You can color these differently, all right, but then you haven't used all three colors. And unfortunately, it's even worse than that, because three-colorability is not invariant under the Reidemeister moves. You see, if you do a tongue, then the third color appears, and this is three-colorable, and it's just another projection of this link. And the problem obviously comes with this tongue move, where when you had a knot, the third color was already somewhere else, but here it needn't be. But luckily, there is a very simple invariant which will distinguish between this linked pair and this unlinked pair.
And this invariant is called linking number. Intuitively, it measures the extent to which two components are interlocked with each other. Well, let me define it. If I have one component linked with another, what I do is I take a conventional direction, and then I just count the number of times this component goes over the other one. Well, here it goes under, so I don't count anything, but here it goes over once, under, over once, so I get a linking number of 2. Well, that sort of agrees with our intuition. Let's look at this case now. Let me again take a conventional direction in this sense, and here it goes over once, and here it goes over a second time. So again, it appears that I've got linking number 2. Well, that certainly is non-intuitive, because these aren't linked together. But in fact, I haven't been very precise in my definition. You see, linking number has a sign to it. So what I must do is, I give a sign to both components, and then I count. Then, for example, in this case, if I'm going in this direction, and then I have a sign there, well, if it's coming underneath from the left, I count +1. So here I have a component, contribution +1. And now coming back in the same direction, you see at this cross, it goes over all right, but the lower one is coming below from the right, so that's -1. And so the total linking number in this case is not 2, but 0. That's a bit better. And if you check the first case, you'll find that, in fact, 2 is correct. Well, what I've got to show is that this linking number is preserved by the Reidemeister moves. Well, let's see. Well, here's a single twist. I mean, it's a single component. It can't do anything to linking number. That linking number relates one component to a second one, so there is nothing to prove here. There is no contribution. Well, what about the tongue? Well, actually, I don't have to prove anything here either, because, look, this just corresponds to the case I have here. This is just a tongue, and you've already seen that the contribution to the invariant is 0. So, again, the tongue doesn't affect anything. Now, what about the slide? Well, again, this is a bit more complicated. There are lots of cases. So let's take a case where this is one component, and I'll assume that the other two refer to a second component. So these two are from one single second component, and I'll assume that the directions are this way and that way. Now let's see what the linking number is. Well, the contribution here, this goes over, and this comes from the left below, and that's +1. And up here, in this case, it's coming from the right, so that's -1. So I get +1 and -1. So the contribution to the invariant is 0. Well, let's see what happens when I perform the slide. So let me put my directions in. And let's count. Well, this is coming from the right, so I have a -1 here, and this is coming from the left, so I have a +1, and I get -1 +1. I get the same 0 contribution as before, but all that's happening is I'm adding the numbers in a different order. So in fact, the slide again preserves the linking number. So what I've shown is that the 3 Reidemeister moves don't affect the linking number.
So we can use the linking number to prove that these really are linked, because you see here the linking number is obviously 1, whereas here for the unlinked circles it's obviously 0. So the linked circles aren't the same as the unlinked circles. And actually we've got quite a powerful invariant, because we've got a whole integer range of values for the invariant. It can be any integer, unlike 3-colorability, which is either off or on. But unfortunately, linking number doesn't do everything you'd like with links. Here's an example of a link of 2 components which has linking number 0. If you count the linking of the red with the blue, then at these 2 crossovers you can see that the signs are going to be opposite, so the total contribution is going to be 0. But it is a genuine link. In fact, you can manipulate it how you like, and it'll always remain linked. It's quite an interesting link. It's called the Whitehead link. Well, it can be proved that it's linked, but we're not going to do it. But what you need is a rather subtler invariant than the linking number. And unfortunately, 3-colorability doesn't prove everything you'd like to prove about knots either. You remember this example that I proved was not 3-colorable earlier? Well, that means we can't prove that it's knotted. But in fact, if you take the rope copy, it's pretty clear that it is knotted. And you can try this at home. In fact, it's what's called the figure of 8 knot. So what we'd need to prove that this was knotted, we're not going to do it, but what we need is a rather more subtle invariant than 3-colorability. And we'll need an even more subtle invariant to detect the linking of this link, which is a link of 3 components, called the Borromean rings. It's a very beautiful, symmetrical link. But what I want you to notice about it is the fact that any 2 of the components are unlinked. You can see it very clearly if you pull it like that, you see. Those 2 are unlinked. It doesn't matter which 2 I take. You'll always get that they're unlinked. And in fact, this generalizes. Here I have a link of 10 components, which has the property that if you remove any one, then it's unlinked. I'll remove the top component, and then it just comes to bits.